The original cotangent of x function looks similar to tangent, except it goes from here to here, roughly like that, with vertical asymptotes at x equals 0 and x equals pi. Now, a confusing thing about Newton is that this could be considered a starting point for cotangent. This could also be considered a starting point for cotangent, starting from over here, okay? But you should always, when you use your answers for Newton, you should always consider this the starting point and not this one over here. Even though they're both part of the graph of all of cotangent of x. It's just kind of a confusing way of their software working, is that we have to consider this the starting point because, and by the way, this is negative pi, sorry, this is pi over 2. Right, because cotangent is between 0 and pi for its first wave, and it's centered at pi over 2 on the x-axis. So that's important because when you do a horizontal shift like this, plus pi over 6 tells you to go pi over 6 units to the left. Okay, so Newton needs you to move it in that direction. So we start on pi over 2, but we need to go pi over 6 units to the left. So I'm subtracting pi over 6 units from it. If you do that fraction arithmetic, this is multiply the top and the bottom by 3. So that's 2 pi over 6, or what is that, pi over 3 for a final? I think that should be pi over 3. Okay, so that's the horizontal shift. We start at pi over 2. We went pi over 3 units to the left. Okay, there's no change to the period. If there is a number here, like a 2, your period of tangent and cotangent isn't 2 pi divided by b, it's pi divided by b. So if there's a 2 there, you'd plug in a 2 to find out your new period. This one is a 1, so the period is still pi. That means I need to be pi over pi units from start to finish on this wave. In other words, my center is pi over 3, so my left vertical asymptote should be minus pi over 2 units away. And so that's 2 pi over 6 minus 3 pi over 6, so that's negative pi over 6 is where one of the vertical asymptotes should happen, like this. Okay, and then the right vertical asymptote is pi over 2 units to the right. But again, that's because my period was still pi. If this is a 2, your new period is going to be pi over 2, and you're going to be adding and subtracting pi over 4 units from both sides, right? Because added together, the distance from one vertical asymptote to the other needs to be the length of whatever your period is. 2 pi over 6 plus 3 pi over 6, that's 5 pi over 6. And so those vertical asymptotes contain our graph, and that's a full period in between. So we're taking care of this. Times 4, I think we're going to deal with that when we have to plot a specific point, so we'll wait on that in just a second. The minus 3 says that, hey, instead of starting here on the x-axis, you're going to go minus 3 units. So you're going to go down, a vertical shift of minus 3 units. So you should have a dot here, and that's where the fluctuation is going to occur. Okay, so we're getting close, and I remember in Newton there's like one dot you can grab and drag to move. So wherever that dot is, you're going to have x and y coordinates, right? So let's say the dot is here where y equals 1. Well, if that dot really is on our graph, then you should be able to plug in 1 into the original equation in for y and then solve. Okay, so if I add 3 to both sides, I've got 4 equals 4 cotangent of x. Any cotangent of x plus pi over 6. But real quick, just to emphasize, the dots that you can move after you get the vertical asymptotes correct, and after you get this center dot in the correct spot, wherever you move those dots, you better be able to plug in the x and y coordinates and get out a true statement in here, or else that dot isn't in the correct spot. Right? So I plugged in y equals 1 because that usually is one of the key dots that they want. If I plug in y equals 1, let's find out what the x coordinate is. I'm going to divide 4 from both sides in this equation. And then I'm supposed to say the cotangent of I'm supposed to say the angle, so that the cotangent ratio equals 1. And remember, cotangent is cosine over sine. So you need cosine and sine to be the same thing. That way when you divide them, it makes 1. That happens at a 45-degree angle. Because if you draw a 45-degree angle in the what's that called? In the unit circle, then you've got square root of 2 over 2 and square root of 2 over 2 here. So the sine ratio and the cosine ratio are the same. So we need this to equal 45 degrees. This angle needs to equal 45 degrees. So x plus pi over 6 needs to equal 45 degrees. In other words, pi over 4 in radians. Yeah. So subtract that pi over 6 from both sides. And we need common denominators. So this is 3 out of 12 subtracted by 2 out of 12 pi. So that's pi over 12. So at y equals 1, we need to be at pi over 12 on the x-axis. Okay, I think I got the right answer here. So there's pi over 2. So then this would be pi over 4. And then this would be another half would be pi over 8. So pi over 12, that looks to be right around pi over 12 for that blue dot. And you see they got the vertical asymptotes correct. The black dot, I don't remember what that does. This is what a student attempted. Oh, the black dot's just the vertical shift. So I guess that -3 we saw, you don't have to adjust the dot right here. You just have to bring the graph down 3 units. So that's roughly the sketch of the graph that we were getting here, right? Just that last dot, you have to make sure that wherever that blue dot goes, it's an actual coordinate on the graph. And another way to check these is to go to desmos.com/calculator. Okay, but whatever graph you're going to submit on, you got to make sure that the dots you've chosen are actually dots on whatever graph you type in desmos.com. Okay, I usually don't recommend desmos.com for solving these because we want to know how to do it without a graphing calculator, but these are really tough. These are the toughest problems probably in the course actually, just to get right in Newton because there's so many little details.